All right, so let's get started. Thank you all for coming once again. So in this lecture, we are going to look at things that are not like cakes, which are indivisible, and that would force us to revisit what fairness means. And we will see how to do that. We'll define new fairness notions, come up with new algorithms for achieving those fairness notions, and have some fun. Okay, so let me first sort of formalize what setting we're working in. So once again, we have the set of agents. And this time, instead of a cake, we have m indivisible goods. So we'll use capital M to denote the set of all goods, and the goods themselves are, say, G1, G2 to Gm. Now I need to tell you how the preferences of agents over these goods are specified. This time it's going to be much simpler. So the valuation functions is simply a set function. So this means the space of all subsets of the set of goods. Okay. Are people familiar with this notation? 2 to the set. Okay. And this is mapped to some number. And as before, we are going to make certain assumptions of the valuation function. The first one is additivity. Note that in general, if I have to fully specify a valuation function, I need to give you the numbers for all the subsets, 2 to the little m subsets. Yes, that's a lot of information. So we are going to make the additivity assumption, which will significantly reduce the amount of information that is required to specify a valuation function. So for any subset of the goods S and any agent I, the valuation of agent I for the set S is what? If it's additive, then what should it be? Louder? Yeah. So S has a bunch of goods. It's just a sum of the individual goods in that set. Okay? And notice that as soon as we make this assumption, we only need to specify m numbers instead of 2 to the m numbers to fully capture the preferences of an agent. It's much more succinct. Okay? And the other one is non-negativity. Which is easy. So for any good G and any agent I, Vi of G, the set G actually, is at least 0. I don't need to specify it for every set because of additivity. Right? Okay. And once again, exercise, prove a monotonicity relation. The more goods, the better. Okay, so think of two sets of goods S and T, where T contains S. Prove that the value for the set S is at most the value for T. Okay. So so the input to any fair division algorithm is going to be n numbers per agent. Okay, so think of the input as being a matrix. The rows are agents, the columns are the goods, and you have n times m numbers specified as the input. Okay, and the desired output, the object that we are going to work with, is going to be an allocation. Instead of a piece, this time we have an allocation. this is say an allocation A, A1, A2 up to AN. So this is simply a partition of the set capital M. Okay, so each AI is a subset of capital M, and no two AI or AJ do not have any element in common. Okay, so the union of AIs is the set M, and AI intersect AJ is the empty set for every I and J. All good? Okay. And once again, the goal is to find a fair allocation of the set M among the n agents. And we are once again going to define a bunch of fairness notions. So let's try to recall some of the things that we already know. The first one is proportionality. So an allocation A satisfies proportionality if what happens? So what did it mean for an allocation to be proportional in the cake world? One over nth fraction, right? If you have n agents. So what do you think should be the definition, corresponding definition in the indivisible world? Right, right? Yes. It will be implicit. I'm not assuming right now, but if you have fewer goods than agents, then someone is going to be empty-handed. So it's not a very interesting problem that way. Yes. So no normalization right now. Uh, so exactly, exactly. So two correct answers. Uh, so an allocation A is satisfies proportional if for every agent I, the value that it gets for its own bundle is 1nth of its value for the entire set of goods, which is Vi for the set M, and like you pointed out, this is simply Vi of G1 plus Vi of G2 plus Vi of G3 and so on. Okay, for the cake it was 1, but today for this lecture we won't need that. Okay, there was one more notion that we studied, which was envy freeness. How do you define envy freeness for indivisible goods? Same definition, exactly. So for every I and J, it should be the case that Vi of AI is at least Vi of AJ. Okay. So does a proportional allocation always exist? Like someone pointed out, what if there are fewer goods than agents? Think of one good and two agents, and say both agents value that good at some non-zero number. Yes? Does a proportional allocation exist? No, right? Because someone has to lose out. That agent gets a utility of 0. I'm assuming that Vi for empty set is 0. Okay, that's the normalization, if you will. And that's not proportional, right? So proportional allocations for indivisible goods fail to exist even in super simple settings. Okay. How about envy-freeness? Same example, right? Some agent is losing out on a good, the other agent gets it, so I'm going to envy that other agent, right? So even in this super simple setting, there's no proportional allocation, there's no envy-free allocation. And when that happens, we need to redefine the problem. So that's what we'll do. These are too strong benchmarks. We cannot meet them always. So we'll try to define benchmarks that we can hope to meet always, if possible. And basically the bulk of the lecture is about algorithms that actually construct such allocations. So uh, here's a relaxation of envy-freeness. It's called envy-freeness up to one good. It's EF1 for short. So this was EF, this was prop. So what does that mean? It's a weird name. Here's what it means. Once again, we are looking for some pair I and j. Pick any pair. If there exists some good g in the bundle of aj such that once you remove that good from the bundle, the envy goes away. Okay? So the term on the left is the valuation of agent I for its own bundle under the allocation A. Term on the right is valuation once again of agent I, but this is a diminished bundle. We have thrown away one of the goods and now we are evaluating the NP. Okay? If for any pair of agents you can kill the NV just by removal of some good, I'm not telling you which good, some good, then the allocation is approximately NV free in this sense. Okay? For example, the two agent one good case, that's not NV free, but it is NV free up to one good. Everybody sees that? Okay. Okay, so exercise. We know that NV freeness is stronger than proportionality. Yes? How do EF1 and prop compare? Does one imply the other, or are they incomparable? What's the relation? So this is a stronger property, let's set it aside, but what about these two? First of all, an NV free allocation is certainly NV free up to one good. Yes? Everybody buys that? Okay, so these are both weaker than NV freeness, but is one of them stronger than the other? Okay, I mean, I don't want you to construct specific examples, but what do you think? What do you feel about these properties? Does one seem stronger or incomparable? Why? Why do you think it could be incomparable? Just give me like the thought process. Mm-hmm. Right. So maybe the envy could be killed by removal of one good, but you're saying that still the fraction of the total goods that you get for yourself is not 1 over n. It's smaller than 1 over n. Is that what you're saying? Okay. Okay. So let's look at an example. So that's actually right. That intuition is correct. And here is an example of an allocation that is EF1 but not prop. Okay. So two agents, 1 and 2, and three goods, G1, G2, G3. And here are the valuations. Okay. And suppose here is an allocation of it. So agent 1 gets G1, agent 2 gets G2 and G3. All right. Is this allocation EF1? Whoever is nodding should explain why. Okay, is it NB free? Yes, go on. 2 is not envious of 1. Why? Because 2's value for 1's allocation is 1 and 2's value for its own allocation is 1 plus 1, which is 2. So 2 does not envy 1. What about 1 envying 2? Mm-hmm. Yes, would be very happy. Yeah, exactly. Exactly. So 1's assessment of its own bundle, this term here, is 10. 1's assessment for the bundle of 2 is 100 plus 1, 101. Right? For G2 and G3 put together. So 1 surely envies 2, but that envy would go away once you throw G3 out of that bundle. Then 2 is only left with G2 and it is smaller than 10. Everybody sees that? Questions? Okay, so this boxed allocation is EF1 for sure. Is it proportional? For 1 it is not. And the reason is, yeah, 1's total value is 111. Proportionality would mean it should get at least half of 111, but it's not getting that. Right? All good? Okay. Yeah. Yes, yes. So this is not, I'm not saying this is the fairest allocation for this instance. I'm saying that there exist instances and bad allocations such that the implication does not hold. Good point. Yeah. What about the other direction? Prop implying EF1. First of all, what happens with two agents? Remember, for two agents in the cake cutting world, these properties were the same. Is that true for indivisible goods? Sorry? Yes. Yeah, EF and I'm asking EF and prop. So for cake cutting, EF and prop were the same for two agents. What about the indivisible analog of that? Prop would imply EF. Why? Same reason. Just spell it out. Okay. Yes. That means any agent is getting at least 50% of its total value for the entire bundle, which means the other agent in its assessment is getting less than 50%. So do you envy the other agent? No, right? Okay. So perfect, exactly. So for two agents, we cannot hope to construct a counterexample. So we need more agents. Let's think about three agents. Okay. And turns out for three agents, you can construct very easy counterexamples. Let me give you one with four agents because that's what I've written it for some reason. So here's a very simple example: four agents and say 5 goods. And note that I'll only need to specify the valuation of agent 1. I only need to specify this row of the matrix, and you'll see the counterexample immediately. And this, and I don't know what this value is, but these goods go to 2. Other values don't matter. So what's happening is there are 4 agents, 5 goods. G1 is going to agent 1. G2, G3 are going to agent 2. And I don't know where G4 and G5 are going. Maybe to these guys. Is this proportional for agent 1? At least. It is. Right? Because this is 4 and 5.5, right? That's the total value. You need to divide it by 4. That's only less than 1.5 because 1.5 times 4 is 6. So it is proportional. And let's say the other goods are such that you can ensure proportionality, but this is certainly not EF1 because so this is the value for the goods that agent 2 is getting. Even if you remove one of them, the NV does not go away. Okay, so prop does not imply EF1 in this example, and you can complete the matrix to make sure that this is the case. Okay, so they're incomparable, which is good. Here's one more fairness notion. It's called the maximin share, or MMS for short. And I have to say that this has the most interesting definition of all the fairness notions. So let's see what it is. So remember that proportionality is specified in terms of a threshold. Okay, once an allocation meets that threshold for every agent, it is proportional. Okay, this is an agent specific threshold. If an allocation meets that agent specific threshold for every agent, it's a proportional allocation. Okay, something similar will happen for MMS as well. It is going to specify a threshold for every agent. So we say that an allocation A is MMS fair or simply MMS if the utility of every agent is at least some threshold. This is for every I. Okay, I'll tell you what the threshold is, but if the threshold is met, then the allocation is said to be fair in this sense. So what is this mu I? So the way mu I is defined is in terms of a discrete analog of the cut and choose protocol. Okay, so say there are n agents. Okay, this is just a thought experiment that agent I is doing. Agent I is looking at all of these goods. There are n agents overall. Now suppose agent I gets to cut the set M into n bundles, which means that there are little m number of goods. It needs to pile them up into little n number of bundles. Okay, one for every agent. It is creating some partition. Now the game that we are going to play is that all the other agents come one by one and start picking a bundle each. Okay, and I gets the leftover bundle. Everybody with me so far? This is just a thought experiment. Agent I is imagining this, that it has piled up these goods into n piles, and people keep on coming in, take the bundles. I is left with the remaining bundle. Now, I gets some utility because of that bundle, and in the worst case, I gets the worst of those n bundles. Right? Might happen. Now, I's task will be to create a partition such that even if it gets the worst bundle, that value is as high as possible. Okay? It is trying to maximize its worst case utility. If I gets to be the cutter, okay, that is mu sub I, that utility. So formally, mu sub I is this thing. It's defined as, so say the allocation that I creates, the optimal allocation that I creates is some capital A, and the bundle that I is left with is the worst bundle in A. Okay, so its utility would be min over k of vi of ak. This is the utility when you get the worst bundle in allocation A. All good? Now I's task is to create an A that maximizes this number, right? So mu I is the max of this over all the allocations A. So let me use like this calligraphic A to denote the space of all partitions. Okay, find a partition A which maximizes the worst case utility. That's the maximum share of agent I, mu I. That's the threshold. Is the definition clear to everybody? Okay. So every agent performs this thought experiment. Okay, they create some allocation which gives them some utility. It need not be the case that the same allocation meets the threshold for every agent. Okay, maybe while doing this thought experiment, agent 1 created some partition, agent 2 created some other partition, agent 3 created some other partition, and so on. Right? It is by no means obvious up until now that a single allocation can give mu1, at least mu1 to agent 1, at least mu2 to agent 2, at least mu n to agent n. Is it not obvious to everybody? That would be good. Okay. And turns out that's not always the case. So there may not exist an allocation which actually meets that. So MMS is not guaranteed to exist. So our intuition was correct in this sense. Okay, there exists some weird, very sophisticated fair division instances, even with 3 agents and 4 goods, but very complicated valuations, some weirdly specified numbers, such that there is no single allocation which meets the threshold for every agent. Okay. But just so that we understand the definition well, let's do an example. So this example has 3 agents and 5 goods. And here are the valuations: 6, 6, 4, 4, 4, 6, 3, 3, 3, 0, 6, 6, 12, 6, and 6. Now question number 1, what is mu1? So recall that agent 1 is doing a thought experiment. It has 5 goods. It has to put them into 3 compartments such that its worst case utility is maximized. How to do that? Give me the names of the goods. B and C together, and D and E together and A. So what's the utility there? 6, 10 and 8. So 6 is the worst bundle. Okay, and why is this, why can't you do better? Right, yeah. So that's right. So basically you need to prove that no matter what allocation 1 creates, the worst bundle will have a utility of at most 6, and the allocation that was suggested actually meets that. So mu1 is equal to 6. What about mu3, third agent? That should be easy. Yeah. What about mu2? Does everyone see why it is 12? This is one bundle, this is another bundle, this is another bundle. Okay. Mu2, 3. What's the allocation? C and A. Okay. Someone say the entire allocation. CD, A and BE, right? Yeah, so BE, that's 3. CD together is 6, A together is 6, and convince yourself that you cannot do better. Okay. So is there an allocation that meets all of these 3 numbers? You've already suggested that allocation. Consider this. Yes? No? Maybe? Sorry? It's even better, exactly. So agent 1 is getting 6, agent 2 is getting 6, which is better than mu2, right? And agent 3 is getting 12. So a single allocation meets all the 3 thresholds. This is MMS fair allocation. May not always exist, but it exists here. Okay, there's another interesting thing about this allocation. So, okay, we write it. A is fair in the MMS sense. Is it proportional? Yes. It's not proportional. Why? Where does it fail? Yes. Why? Why does it fail? What's the proportionality threshold for 1? 1 is 8, right? And it's 6. So not proportional. So MMS need not imply proportionality. You know the next question. Does proportionality imply MMS? So notice that both proportionality and MMS are defined in terms of thresholds, right? Suppose there is an allocation that meets the proportionality threshold. Does it meet the threshold for MMS? Right. Proof by example. So this is just one example where it is true, but is it true in general? So, okay, let's think about this. Let's go back to the thought experiment that agent I was doing. It was creating this partition and gets the worst bundle. What is the utility of the worst bundle in comparison with the proportionality threshold? Proportionality is the sum of everything divided by n, and if you're getting the worst bundle, can it be more than n, a 1nth fraction? No, right? It has to be at most the 1nth fraction. Everybody buys that? Let me repeat. We are revisiting the thought experiment that agent I did. It created these n bundles somehow, right? And it gets the worst of those bundles. Now, what is its utility for the worst bundle? It cannot be more than 1nth of the total utility because every other bundle is at least as good. So if you sum them up, it will exceed the total utility for all the goods, right? So that's not happening. So proportionality threshold is an upper bound on the MMS threshold, right? Is that correct? Okay. So if an allocation is proportional, it better be MMS. Okay. So in that sense, MMS is like a relaxation of proportionality. We already saw a relaxation of EF, which was EF1. This is in some sense a relaxation of proportionality. You're sort of lowering the threshold for every agent. All right, so here's the sort of the summary, the picture that you should keep in mind. So EF is the strongest fairness notion. It implies proportionality and it also implies EF1, and we know that this is incomparable because the examples, right? Proportionality implies MMS. Okay. Try and think about the relation between EF1 and an MMS. Okay. The hint is that if you have been paying attention so far, you should know the answer already. All right. So complete this link if there's any. Alrighty. Oh, we are going on. We're going well. So this is all I had to say about fairness notions. Now I'll get into the existence and computation part, but are there any questions up to this point? Question? Okay. So, okay, let's get into the existence results. We have already seen a few actually. So we already know that EF may not always exist, proportionality may not always exist, right? MMS, I have told you it does not always exist, but I haven't given an example because it's quite complicated. And I encourage you to look at the references on the web page to for the example. So EF prop MMS may not exist always, but there's a reason EF1 is on the board, because EF1 always exists. Okay, and we are going to see not one but two proofs of this fact today. Okay. So let's see how we can find fair allocations. We'll start with a somewhat of a disappointing result. So two agents and identical valuations. Identical valuations means that the rows are all identical. So the numbers within each row might be different, but every row is just a copy of the other. Okay. So even with two agents and identical valuations, deciding whether there exists an NP-free allocation is NP complete. Does everyone understand what NP complete means here? Okay. All right. So we already know that EF may not always exist, but the question is, can we find it whenever it exists? And turns out we can't do that even in very, very simple settings like this. How do we prove such a result? Maybe someone from this side. I'm trying to be fair to both sides. Uh, Someone shouted the right answer, but can you do it again? Reduce this to something or something to this? Something to this, right? What is that something? Do you have any ideas? So what problem involves a bunch of numbers and dividing subset sum or partitioning, right? So does everyone see a reduction? Think of the partition problem. Okay, you're given n numbers and you have to separate them into two halves such that their sum is the same, right? Can you reduce partition to fair division? Numbers are the valuations. They are identical. So both agents have the same. So okay, you're given n numbers in partition. That's as many goods as they're going to be in the fair division instance. Each number is the same value for both the agents. And how do you infer Beefiness from partition? So what does a valid partition mean? Yes. Yes. Right. So right. So basically these are two numbers that have a constant sum and you're trying to maximize each of the halves. They're maximized when sort of they're equal, and that's the partition. Okay. Okay. I'll I'll not say anything more about it, but try and work it out. It's a very simple reduction. Okay. So the prof is exercise. Okay. What about proportionality? Can we make a similar statement about prop? So given even with two agents and identical valuations, deciding whether there exists a proportional allocation, is it NP complete? Same reduction. Two agents, NP-freeness and proportionality are the same properties, right? Okay. Here's the more interesting bit. So now we want to move to MMS. We want to think about the computation of maximum share. But this reduction might not work as is, because with two agents, I claim that an MMS allocation always exists. And I don't even need identical valuations. Could be not identical, but MMS always exists. Can anyone think of why? Say it again. Yes. Yeah. Yes. Yes. That's right. Yeah. Yeah. So that's. Let me just sort of rephrase what is said. So once again, let's go back to the thought experiment. Once again, let's think about the partition that agent 1 creates, say, okay, and if it's getting the worst of the two bundles, and the value of that bundle is mu1, so that's that. Let's say, I claim that actually this allocation is an MMS allocation, um, and that's, I guess, the point. Sorry? Right, right, yeah, either of, yeah, both of them work. Yeah, so agent 1 has created some allocation A1, A2, okay, and say V1 of A1 is at most V1 of A2, so this thing is mu1. So A is that special allocation that agent 1 creates. Okay. So let's actually run a cut and choose for these two agents. Okay, like not just do a thought experiment. Let's actually run it. So is that true? Say agent 2 is picking A2, agent 1 is left with A1. Uh, no, hang on. Yes. Right, right. What's the formal argument though? This is not correct. Let me think about it for a second. Can you write it down?
So let's say that V2 of V2 is greater than V2 of V1.
That's an assumption.
Yeah, so
Okay.
this A2 is arbitrary and to the same
Yes.
A1. So we know that this will now be greater than the summation of V2.
This is at least the proportionality,
Yeah,
which means exactly.
at least half of this.
Yes.
And the threshold can't be more than this.
Right.
U2 can't be more than half of this.
Right.
So if agent 2 picks A2
Yes.
as his partition,
Yes.
he satisfies the threshold.
Yes.
And agent 1, any of the threshold, any of the partitions that he gets, he's happy with that because this
Yes.
was the
By definition, it was the MMS partition.
Yeah.
Okay. Thanks. Does everyone get the argument? Okay, I'll just repeat the argument. So allocation A is the partition that agent 1 created as part of its thought experiment. Okay. And say it ended up with bundle A1. Say we are actually running the cut and choose for these two agents. Okay. Say it ended up with this, which means agent 2 picked A2. Why did it pick A2? Because what he wrote actually what I raised. So V2 of, right? Because it is picking its favorite bundle. So this is at least the proportionality threshold. Proportionality is at least the MMS threshold. So the same allocation meets the MMS threshold of both agents. Questions? Okay. Yeah.
simulated with the valuation function of the other agents?
No, no. Thought experiment is always with respect to your own valuations.
Agent 2 should have given A1 first. But
Yeah. By definition, agent 1, the bundle that agent 1 is left with is the worst bundle. Okay, which means agent 2 has picked its favorite bundle. So, that's it. Is that your question? The answer is okay, fine. Okay. Yes, agent 2 picks bundle according to V2, agent 1 does the thought experiment according to V1. Yeah. Okay, so try and complete the proof. I haven't written it fully here. Uh, but what I want to convey is that for two agents, an MMS allocation always exists. Okay, so a problem that always has a solution guaranteed, can it be NP complete? Note that there is no instance anymore. Like every instance is a yes instance. Okay. So here it turns out that the computational difficulty is coming from a slightly different source. Uh, the difficult part is determining the value of mu, the threshold for every agent, MMS threshold, mu i's. Okay. So even with two agents and identical valuations, deciding if mu I, which is the MMS threshold of any agent, whether this is bigger than some input theta, is NP complete. Okay. I didn't catch the question. I care about whether this is true or not, but this is a way of framing like what mu I is. I can just do a binary search over theta as to. Mm-hmm. Yeah. Right, but can you do it efficiently is the question. You need a partition, exactly. It's the same reduction. It's the same reduction. The threshold theta reduction is the half of the sum, total sum. Because if the worst bundle is half of the total sum, the total every bundle is half of the total sum, so you're effectively looking for a partition. Exactly. Yeah. Yeah. So, yeah, with cake cutting, the computational difficulties in terms of the queries, in terms of the information content. Here we have all the information in terms of this matrix. The difficulty is in computing a partition. So that's the source of hardness for many of these things, and that's what I think Neil is also pointing out. I hope. Is the statement clear? Fantastic question. So, okay, I think I had written up this as a puzzle for everybody. So go and think about it. Okay. Uh, Suppose I promise you that whatever fair division instance I'm going to give you has an MMS partition. Okay. I give you only the instances which admit some MS partition. I'm not telling you what partition it is. And I also, for free, give you all the mu i's, mu1, mu2 up to mu n. Okay. Now I ask you to go back and come back with an MMS allocation that meets a single allocation that meets all of these thresholds. Can you do that in polynomial time? Is there an algorithm for achieving that? Write it up, and show me the proof. No, 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 not two agents. Sorry. N agents. Yeah. Okay. This question is valid for all, like any general value of n. Yeah, yeah, yeah. But I'm not guaranteeing you proportionality. I'm guaranteeing you something weaker. I'm only guaranteeing you MMS allocations. Okay. I also give you the mui's for free. Now find an MMS allocation. Okay. So note that you cannot say no anymore because I'm giving you the promise instances. So okay, all right. Think about it. So let's get into the algorithms now. So two algorithms and then we'll be done. And both algorithms, like I promised, are for EF1. So the first algorithm, I'll just call it alg1. It is a very simple algorithm that I'm sure we are all aware of. It's the greedy round robin. So the way this algorithm works is as follows. You fix an ordering over the agents, 1, 2, 3 up to n, fix some order. Now agents say all the goods are placed in a room. Each agent enters the room, picks its favorite good and leaves the room. Next comes the other agent in the order, picks its favorite good from among the remaining ones and leaves the room, and so on and so forth. When all agents have had their turn, we cycle back to agent 1. Again it enters the room, picks its favorite good and leaves the room. This goes on until all the goods are exhausted. Okay? Now while I write the algorithm, try to think of why it might be F1. Thoughts? Yes?
We can prove it by induction that at the end of each round the algorithm is universal.
Okay. Why?
Because whatever you are picking, I mean whatever others have picked now, there is at most one object which is valuable than the object you have.
Great. So that's pretty much the argument. So the claim is that the allocation that results from this algorithm is EF1. So alg1 outputs EF1 allocation, and the proof is by picture. So here's round 1. Agents keep picking some goods. Then again you cycle through the agents, round 2, on and on. So when we are talking about EF1, we need to fix some pair of agents I and j. Okay. So say first let's consider the case where I is ahead of j in the ordering. So I gets to pick a good before j every single time. And say I picks some good g1 in round 1 and j picks some good g1 prime in round 1. Round 2 again, g2 for I, g2 prime for j, on and on. And maybe in the final round, say I gets to pick some gk and maybe the goods are exhausted by the time it's j's turn. We don't know. Okay, I mean you can call it g prime k. If j does not get a good, think of it as a zero valued good. Okay. So every single time, round by round, I gets to pick a good before j. So good by good, I likes its own bundle better than that of j, right? Because at this point I had the choice of picking either g1 or g1 prime, but it chose to pick g1. Why? Because it liked that better. So good by good, I think that its bundle is better. Is the argument clear to everybody? Correct? Okay. What happens if the order is different? So this time j is ahead of I in the ordering, right? So in the first round j gets to pick g1 prime first, then I gets to pick g1, then g2 prime, g2, on and on, some gk prime, and maybe I doesn't get to pick a good, whatever. Now notice that, so this is for j, this is for I, this is for j, I, j, and so on. So let's forget about this part for a moment. Okay. When it is I's turn, it had a choice to pick either g1 or g2, g2 prime, right? But it chose to pick g1 over g2 prime. So except for the good g1 prime, good by good, I likes its own bundle better than that of j, except for one good. Is that clear to everyone? Okay. But what does that mean? It is EF1, right? So if I remove this good g1 prime, the NV surely goes away. Okay. So Vi of AI is at least Vi of AJ with the possible removal of g1 prime. Either way, A is EF1. Correct? Okay. One thing I want you to notice from this proof is I'm making a crucial use of additivity here. When I say that good by good, an agent likes its own bundle, and when I say that that's the reason why it likes the total bundle better than the other total bundle, that's possible because of additivity, right? So the next algorithm, the final algorithm for today, is going to drop that assumption. It is going to show that EF1 allocations exist even without the additivity assumption. Mm-hmm. What matters?
So inside the round,
Uh-huh.
change the ordering of the elements.
Yes.
Then this proof is not going to work.
So you have to fix an ordering before you do the round robin.
After that, you within a round of
Well, then all bets are off. So maybe yeah, I mean, then I's favorite good could be picked up by someone else. You can't make these good by good arguments for any pair of agents, right? Uh, in that fixed order, yes. So there's a queue of agents, like 1, 2 up to n, and I occurs before j in that queue. And you always respect this queue when you do a round robin. But I think the question is that what if you flip around agents in that queue? Um, then it need not be. Maybe I likes it's good better. I likes it's good over j in round one, but for all subsequent rounds it does not. So you can't make these good by good kind of comparisons. It's not clear. Yeah. Yes. For all those rounds, yes. Yes. But the thing is, okay, so maybe for some fixed pair of agents you can do this, but EF1 is a property that is true for every pair of agents. So there has to be some way of guaranteeing this for every n choose each of the n choose two pairs. So that's not clear how to do that. Yeah. Maybe, I mean, maybe one can do these tricks, but it would be not as clean as this. Not certainly not as simple as this. What does this say about MMS? So I can tell you that it gives you an approximate MMS. I haven't defined approximate MMS yet, but let me do that. Why not? So, an allocation A is MMS if it meets the threshold mu I exactly, like at least mu I for every agent. You can also define alpha MMS allocations as ones which meet alpha fraction of this threshold. So for every agent, an allocation that guarantees 50% of mu I is half MMS. Okay, and here's something that we can add to this picture. Any EF1 allocation is guaranteed to be 1 over n MMS according to this definition. So this is 1 over n. Okay, again a nice exercise. Try to prove this. So now to answer Neil's question, because we have an EF1 allocation, we also have a 1 over n MMS allocation. Questions? Okay. So let's move to the final algorithm of the day. Al2. I don't know what the name is, but you can just call it the NV graph algorithm. And it is due to Lipton et al. From EC04, is it? I don't have it written up the year. Okay, let's call it EC04. Might be off by a year. Apologize for that. Oh. Can I erase this? Okay. So the twist now is, instead of considering agents in some order, we are going to iterate over the goods now. So we'll first give one good to some agent, then we'll cleverly figure out who gets the next good, and on and on and on until we exhaust all the goods. And the way we figure out who gets the good is via a graph called the NV graph. It's a very nice visual tool for fair division problems and very handy. It comes up all the time in analyses, so good to know. Okay, so before giving the algorithm, let me define what NV graph is. So given any allocation A, the NV graph G sub A is a bidirected graph, which means the edges can go in both directions. It's defined over the vertex set, as the set of agents. So the set of vertices are just 1, 2 up to n, and the edges are defined as follows. So here's agent I, here's agent j. We will draw an edge or directed edge from I to j if I envies j in the allocation A. Okay. Now it is possible that maybe j also envies I, in which case we draw the edge in the other direction. That's why it's a bidirected graph. Okay, so I envies j if and only if there's an edge from I to j if and only if I envies j. Okay. So an NV graph can be cyclic. It can have cycles. Does anyone see a way of resolving the cycles? A simple way of resolving the cycles? Yeah, I was looking for that sign. So that's the correct idea. One can do swaps. Okay. So say there is an allocation where there are only two agents, one envies 2 and 2 envies 1. What do? You swap the bundles, right? And the cycle is resolved. And you can imagine that there can be larger cycles, 1 envies 2, 2 envies 3, 3 envies 4. Okay. Once again, you can do this cyclic shift, cyclic swap operation, or like a toggle operation, and the cycle is resolved. Okay. So here's a lemma. Let A be an allocation such that the NV graph G of A is possibly cyclic. Then one can transform it into an allocation B over the same set of goods such that G of B is acyclic, and all of this can be done in polynomial time. Polynomial in n and m, little n, little m. How do we prove such a thing? So let 1, 2, 3, k back to 1 be some cycle in GA. There can be many cycles, and we will resolve them one by one. So the picture is this. So I'm drawing the NV graph here. This edge means 1, NV is 2. Okay, there might be more edges. I'm not drawing them. And so let's call this cycle C. And there might be agents outside this cycle. Those are N set minus C. Okay. Could be a bunch of agents here. They can have edges all over the place. I don't know. But this is certainly some cycle because it's a cyclic graph. Okay. Suppose I use the suggestion of doing a cyclic swap. Okay. So I started with, so this is the NV graph of allocation A. I'm going to transform this allocation by doing a swap. So if you NV some agent, now you get its bundle. So we now have a new allocation B, for which B of I is A of I plus 1 mod K. Okay. Did I get it right? Question? Okay. So B1, the new bundle of agent 1 is the old bundle of agent 2. So because 1 NV 2, now we are giving 1 the bundle that it was NVing earlier. That's the cyclic swap. New bundle of agent 2 is the old bundle of agent 3. Okay, and I need to do a mod because of the cyclic thing. I'm just checking if I got the mod value correct. So if I is equal to k, then yeah, k is getting the bundle of agent 1. So k plus 1 mod k is 1. So bk is a1. That's fine. Okay, and for every, so this is for all the I that were in the cycle. For all the i's, or for let's say all the j's that were not in the cycle, we have this. Their allocation is not changed, right? They are not part of the cyclic swap. Fantastic. Let's try and see what happens to the edges of the NV graph if you do such a swap. Okay. That's the hope anyway, to prove the lemma. Yeah.
You're swapping everything, right?
I'm saying there is some cycle. There could be many cycles. I'm just fixing one cycle and doing a swap for that cycle.
Yeah, but you're swapping between all I and I plus 1 in that cycle, right?
Right.
The thing is, when you swap, let's say between I and 1 and 2, one gets the
Bundle of 2.
Bundle of 2, but then then that arrow will be reversed.
Need not be reversed. So because 2's new bundle,
Yeah,
it's not. So well, yeah. So we'll see what happens. Yeah. Arrows need not be reversed. Okay. So a very high level observation at this point. Every agent that is part of the cycle is becoming happier under B. Yes, because it is getting a bundle that it NV'd before, right? Okay. The bundles of these guys are untouched, so they are just as happy as they were before. Sorry? No, I'm just talking about the utility Vi of AI and Vi of Bi. So for any agent here, the happiness or the valuation is the same between A and B because the allocation hasn't changed, right? Okay. But let's try and see what happens to the NV edges under A and B. So this is how the graph looked like under A. there'll be some shape shifting under B. Let's see what happens. So for any pair of agents that were not in the cycle, both of which were not in the cycle, so case 1, say I is not in the cycle, J is not in the cycle. Let's look at the NV between them before and after, okay, under A and under B. Since the bundles haven't changed, should the edges change? They should not, right? So if there was no edge, there will still be no edge. If there was an edge, there'll be an edge. So no change. No change in the IJ pair. Correct? All right. What if I was not in the cycle, but J was in the cycle? So note that, so say this agent is I, and say J is I don't know, somewhere here. It was part of the cycle, and J gets the bundle of the agent here. Exactly. Note that NV is defined with respect to bundles, not with respect to agents. Identity of agents does not matter as long as the bundles are fixed, right? You do not envy agents, you envy bundles. So J's new bundle is J minus 1's old bundle, right? So if I envy J minus 1, that edge simply gets shifted to J, because the bundle hasn't changed, only the owner of that bundle has changed, right? So if you think about the cycle as a whole, any agent from outside the cycle who had any edges here still has the same number of edges, they only get shifted around. Okay, the number of edges does not vary, that's the important bit. So number of edges did not vary here, number of edges does not vary even for this case. Why am I stressing on number of edges? Because I'm going to use that as a potential. I'm going to say that the number of edges in the NV graph decreases when you do this swap operation, okay, and I'm just doing a case by case analysis of that. So in this case, edges get shifted, but the number of edges is unchanged, and even here the number of edges is unchanged. Great. So what are the two other cases left? When say I is in the cycle and J is not in the cycle. Okay, so here's the eraser. So this is I now, this is J. Okay, now what happens? Sorry, G's bundle is not changed, and we already agreed that I is becoming only happier. Okay, so for sure no new edges get added. Edges might go away or not, but nothing new will get added, because NV can only reduce from I to any of the non-cycle agents. Okay, so surely no new edges added, and again the number of edges does not increase, could decrease. Oh, sorry, okay. No. So now, so I'm looking at NV from the perspective of I. So, yeah. Right. So the bundles here are shifting, but it is, we have to be careful about whose perspective we adopt when evaluating the NB. So earlier it was this agent's perspective, now it's this agent's perspective. So far so good. The final case is when both agents are in the cycle. That's the most interesting case. What happens now? Sorry, just a second. Um, Let me redraw the cycle here. So say I is here, J is here. Now what happens? Neil, you had a question? Yeah, so all of these edges in the cycle disappear, but but okay, so we have to be careful about uh, okay, anyone wants to say something about this case? Yes, something like that. So okay, once again, first, so say there was an edge like this in the cycle, then under the allocation B, this edge simply gets shifted around. Okay, so the bundles are traveling this way, so this gets shifted around like this, right? So because NV is in this direction, so swaps are in the other direction. So once you swap a bundle in this direction, the new NV is in that direction. So if I NV'd any agent in the cycle, it now NVs the predecessor of that agent. Okay. Sorry, say I'm unable to.
Suppose I get a better bundle from I plus 1 research.
It could disappear as well. Yeah. But certainly no new edges will appear. They'll only get shifted around. Okay. But there's one edge that surely disappears. It's the edge to the agent whose bundle it got. Right? This edge sort of gets absorbed within I. It gets disappeared. So we are killing at least one edge, and no new edges, at least in terms of number, are appearing. They only get shifted around. Okay. So in this case, number of edges has to decrease by at least one. Yes? So by case analysis, whenever we do a cyclic shift operation, the number of edges in the NV graph has to go down by at least one. Okay? So suppose you resolve some cycle by this operation. There might be other cycles in the graph as well. But because of this argument, this process cannot go on forever. Because every time you are creating, you're taking away at least one edge, and there are at most n squared edges in a graph, so you are bound to succeed. Okay. So can people write a proof of this lemma now? There's one subtlety that I did not talk about, but you should be careful about when writing the proof. So it's related to the polynomial time here. So we know that the number of such operations is bounded, but can you find a cycle in polynomial time if it exists? How many people say yes? Can one of those people give me an argument for why? Maybe someone at the back. So if there exists a cycle, can you find it? Traversal time. Okay. All right. Okay. So the potential function is the number of edges, and it must drop by at least one. That's sort of the proof sketch. Try to fill in the details. But that's great. So any allocation with a cyclic NV graph can be at polynomial cost transformed into one with an acyclic NV graph. Okay, so I'm going to give this operation a name. I'm going to call it acyclize. Okay, acyclize. So I'll just call B as acyclize of A. So this is like a subroutine where I input an allocation with the possibly cyclic NV graph, and the output is an allocation with an acyclic NV graph. Okay, it's a sort of a compact term for that. So in other words, it's saying that acyclize is correct and runs in polynomial time. That's what this lemma is saying. But there's one more property about acyclize that is very, very important to us, which is that acyclize operation, and I hope everyone understands what I mean when I write acyclize now, okay? Preserves EF1. What this means is that suppose A is an EF1 allocation with a possibly cyclic NV graph, then we can transform it into another EF1 allocation with an acyclic NV graph in polynomial time. Okay. So is that true? Does acyclize preserve EF1? So let's just think of one swap operation and we can just repeat it for every operation. So suppose A was EF1 here, okay? When I do the cyclic swap operation, does the resulting allocation B also remain EF1? The question is, there's this cyclic swap operation, right? The input to cyclic swap operation is an NV graph and corresponding to an allocation A. Suppose I tell you that A was EF1. Okay. Now you perform this operation, get a new allocation B. Is B guaranteed to be EF1 or not? Intuitively, yes. So, I mean, that's pretty much also the answer. So, everyone is getting happier, yes. So, certainly, if it was EF1 with respect to agents pairs of this form, it still continues to be F1. But you should do a case analysis for every type of pair. Okay. So let me just like sort of say a few words about the proof. I won't write down the proof, but what I want you to observe from the proof, if you write it down, is that you won't require additivity. Okay. In round robin you did, but you'll no longer require it here. So this case is easy. Nothing changes here. So if this pair was EF1 before, it continues to be EF1 now. Here the edges get shifted, right? So if the pair I and j minus 1 was EF1, then the pair I and j in the allocation B has to be EF1. Okay, so the EF1 is inherited from a neighbor, if you will. Okay. What about these pairs? This is what Neil was saying, right? So I is becoming only happier, so NB can only go down, right? So EF1 is maintained. This is the interesting bit again. But again, by a similar shifting edge argument, you can once again argue EF1. Okay? Questions? We are not moving goods around, we are moving bundles around. So that's the important observation. Yeah. You envy bundles, not agents. Good point. Yeah. Okay. So I'll just leave the lemma here. Please go back and prove it and observe that you don't require additivity. That's the crucial bit. But overall, so here's what we have so far. Acyclize. If I give an EF1 allocation as input to acyclize, it gives me as output an EF1 allocation, which has an acyclic NV graph. Okay. Now, why am I so excited about acyclic graphs? What's the one fact we know about directed acyclic graphs? Topological ordering, meaning they have a source. What does a source agent mean in terms of an NV graph? What does it mean for an agent to be a source agent of an NV graph? No one envies that agent. Okay. Now, suppose there is a good that I throw to that agent, right? If the allocation was EF1 before, and if its NV graph was acyclic, and if I give the source a new good, it continues to be EF1. Yes? So now there is a sure shot agent who I can give a good to and maintain EF1 property. And if in this process I lose the cyclic property, I'll invoke this lemma, acyclize it, and move on. Okay? Let me write down the algorithm. Oh, I see, I wrote it there already. Never mind. So step one, this time we are going to fix an ordering over the goods, some arbitrary ordering. G1, then G2, then GM, say. Initially, I have an empty allocation. A is 0, A at time step 0 is all empty sets. Now I'm going to iterate over the goods. So for k equals to 1, 2 up to m, I'm going to assign G sub k to whom? Source of the NV graph of AK, or AK minus 1 actually, right? Because k is 1 here. Okay, so assign GK to the source of, so NV graph for allocation A was denoted by G sub A. NV graph of allocation A k minus 1 is G sub A k minus 1. Okay. Note that an empty allocation is EF1. There's nothing to note. I mean, it is EF1. Okay. So the first time I enter this loop, I have an EF1 allocation with an acyclic NV graph. Correct? If I assign a good to the source, it continues to be EF1, but may no longer have acyclicity of the NV graph. But I have a way to address that. So, okay, first of all, let's call the new allocation B sub k, B super k, and the allocation for the next iteration is simply acyclize of bk. Okay, if the NV graph becomes acyclic, I pass it through this filter. If the NV graph becomes cyclic, I pass it through this filter. NV graph becomes acyclic, and it still is EF1 because of that. Okay, and I repeat. So whenever I enter the loop, I have this guarantee that the allocation is EF1 and its NV graph is acyclic. That is why the assignment to a source of GAK minus 1 is well defined, because the source exists. Okay, just repeat this and return AM as the output. That's the algorithm. Does it make sense to everyone? Okay, so a lot of things I have only sketched here, but you should really write the running time analysis and the correctness analysis formally. So you'll need to prove all of these lemmas in detail, but I'm skipping over that. there's just one last bit, because we worked so hard for the EF1 property, I think we deserve some merit out of that. So I'm going to use either a round robin or NV graph algorithm to actually design an approximately NV free allocation in cake cutting. Okay. It's a very simple algorithm, and here's how it works. So let me define approximate NV freeness first. So just sort of switch back to the cake world for a moment. So an allocation A of the cake is epsilon NV free if so I just add a additive slack of epsilon. Okay. So maybe I NV is J, but when you take away epsilon from it, the NV goes away. That's the idea. Okay. And here's the algorithm. Here's the cake. First, agent 1 comes in and makes a mark for a piece that it values at epsilon. Okay, so it's a cut 1 0 comma epsilon query. That's where it makes a mark. Okay. The next mark is wherever the value of epsilon is realized again. Okay, and keep on doing that. Okay. Basically, chop up the cake into epsilon valued segments. Okay. So this is what player 1 does. Now in comes player 2, it does the same thing. So say player 2's marks are like this. Now in comes player 3 and it does the same thing. Player 4, player 5, player n, everyone makes a mark like that. Okay. So every agent is making 1 over epsilon many marks, okay, ceiling or floor, whatever. So there are total n over epsilon many marks on the cake. Okay. Now here's the cool observation. Look at any interval between any two consecutive marks and treat that as an indivisible good. Okay. So this is one indivisible good, this is another indivisible good, another indivisible good, and so on. Any of these goods is valued at utmost epsilon by any agent. Right? I've just chopped up the cake into indivisible goods. And now run your favorite EF1 algorithm. Okay. So the guarantee that you will get is at least Vi of Aj minus J. For some good J in the bundle of any other agent, this holds true. By additivity, this is this. Yes? This is at most epsilon. So you have an epsilon in free allocation. So exact NV freeness is tricky, but if you relax it to approximate NV freeness, there's a very simple algorithm. There are actually two very simple algorithms. Okay. So good. So that's all I had to say for today.